Let's jump right in. Welcome to This Explainer. Today, we're breaking down a seriously foundational chapter in modern physics. We're looking at how humanity actually learned to control the microscopic flow of electrons, something that absolutely revolutionized our modern world. Honestly, it's an epic story of how we figured out a way to turn regular, everyday sand into the most complex and powerful machines ever built by human hands.
Have you ever actually stopped to wonder how computers shrank from these giant, heat-generating behemoths that filled up entire rooms, down to the sleek smartphones resting right there in the palm of your hand? Well, the answer lies entirely in a dramatic technological evolution. To make that incredible leap, we had to totally transition away from bulky, fragile vacuum tubes and enter the incredibly elegant world of solid-state electronics.
So, here's our roadmap for today. 1. The solid-state revolution. 2. Mind the energy gap. 3. Pure intrinsic semiconductors. 4. The magic of doping. And finally 5. Forming the p-n junction.
All right, kicking things off with Part 1, the solid-state revolution, and how we replaced the vacuum tube.
Picture this. Our story begins in the era just before 1948. This was a time when electronic devices relied heavily on vacuum valves, or vacuum tubes, to control electrical currents. And looking at the left side here, you can really see the stark limitations of that early era. These tubes required extremely high heat. We're talking operating around 100 volts, and they needed completely empty vacuum space inside a glass bulb just so the moving electrons wouldn't literally collide with air molecules. Because of this, they were bulky, they chewed up immense amounts of power, and they were constantly burning out. But look over on the right. Solid-state semiconductors. These microscopic devices guide electrons entirely within a solid crystal structure. There is absolutely no external heating required, they operate on remarkably low power, and they are incredibly reliable. It was a complete and total paradigm shift.
Moving right along to Part 2, Mind the Energy Gap, Categorizing Materials. Okay, so we've always known that certain solids conduct electricity, right? But the real key to this chapter of electronics was finding a material where that flow could actually be controlled. Inside a crystal, electrons exist in these continuous energy levels that we call bands. You've got the valence band, which is where electrons are tightly bound to their atoms. Then you have the conduction band above it. That's where electrons need to be if they're going to move freely and actually create an electrical current. Now, the empty space between these two bands, that is called the energy band gap. Understanding and manipulating this specific energy gap determines literally everything about how a material behaves electrically.
It's actually pretty amazing how neatly nature categorizes materials based entirely on the size of this energy gap. Just look at the metals column on the left. Their conduction and valence bands actually overlap. There's no gap at all, which is exactly why they are fantastic high-conductivity materials. Then, on the other extreme, we have insulators. They have a massive, impassable gap of more than 3 electron volts. Normal electrons simply don't have the energy to jump across that gap, so no conduction happens. But right in the middle, we have semiconductors. They feature this perfect Goldilocks gap, less than 3 electron volts. It's not too big, it's not too small. It is this intermediate gap that allows us to push electrons across when we apply just a little bit of energy.
Which brings us to Part 3, Pure intrinsic semiconductors, also known as the silicon sandbox.
Let's focus in on the actual raw materials that possess this perfect, intermediate Goldilocks gap. The most famous ones, of course, being silicon and germanium. In this incredibly pure or intrinsic state, every single silicon atom shares its 4 outer valence electrons with 4 neighboring atoms. This completely locks them into a very strong, highly stable, 3-dimensional diamond-like covalent lattice. Essentially, every single electron has a partner.
But here's the catch. Because that structure is so perfectly locked together, at absolute zero, intrinsic semiconductors act as perfect insulators. Every single bond is intact. No electrons have the thermal energy required to cross the band gap, resulting in exactly zero electrical conductivity. But obviously, we don't live at absolute zero, do we? When we bring this crystal up to room temperature, the ambient thermal energy actually vibrates the lattice and knocks a few of these bound electrons loose. They gain the energy to jump across the gap and become free to conduct electricity. But look closely at what they leave behind, a vacancy in the covalent bond. We call this a hole. And fascinatingly, because a negatively charged electron is missing, this hole behaves entirely like a freely moving, positively charged particle. Crazy, right? This creates a really fascinating dynamic. A hole actually moves through the solid crystal as a clever illusion of movement. It's kind of like an empty seat in a packed movie theater.
shifting as people slide over one by one to fill it. Neighboring bound electrons jump into the vacancy, which makes the positive hole glide dynamically through the silicon lattice.
All right, let's look at part 4, the magic of doping, engineering the crystal. While the behavior of pure intrinsic semiconductors is definitely fascinating, thermally generated holes in electrons just don't conduct well enough to be useful for making devices. So humans intervened. We use a brilliant engineering technique called doping. This is the deliberate addition of a specific impurity, known as a dopant, in mind-blowingly tiny amounts. We are talking about just parts per million. It's kind of like adding a single drop of hot sauce to an entire pot of chili. By adding that tiny impurity, we dramatically increase the semiconductor's conductivity without warping the overall geometric crystal structure.
Our first specific doping strategy involves adding a pentavalent element, like arsenic or phosphorus, which naturally has 5 outer electrons. 4 of those electrons lock into the lattice perfectly with the surrounding silicon. But that 5th electron, it's the odd one out. It's very weakly bound and easily breaks free to conduct electricity. The dopant acts as a donor, flooding the material with extra negative charge carriers. And because of this negative flood, we call this an N-type semiconductor.
On the flip side, what if we use an element with only 3 outer electrons? Say, a trivalent element like boron or aluminum. Well, because there are only 3 electrons available for bonding, there's actually a missing electron in the lattice structure right from the start. We've instantly created a hole. In this case, the dopant acts as an acceptor of electrons. We call this a p-type semiconductor, which now relies on a massive abundance of positive holes as its majority carriers for the electrical current.
And that brings us to the grand finale. Part 5, forming the PN junction, the ultimate team-up.
So now we have these incredible, highly specialized building blocks, N-type materials totally loaded with negative electrons, and P-type materials loaded with positive holes. When an N region and a P region meet perfectly together on a single silicon wafer, the true magic of modern electronics is born. This meeting point, the P-N junction, is the foundational building block for diodes, transistors, and literally every digital computer circuit on the planet today.
Right at the border where they touch, this dynamic, almost violent microscopic battle takes place. Step 1 is diffusion. Because of the stark concentration differences, electrons wildly rush over to the P side and holes wildly rush over to the N side. But as they do this, step 2 kicks in. They leave behind completely immobile charged ions. This physically strips the border area of any free charges, creating a zone called the depletion region. Then step 3 is drift. That newly formed depletion region acts exactly like an invisible electric fence. It builds up an internal electric field that eventually pushes back against the migrating charges.
Eventually, an incredible microscopic standoff occurs. Once this rapid tug-of-war reaches an equilibrium, a state where the outward diffusion current perfectly balances the opposing inward drift current, the border finally stabilizes. We now have a completely stable PN junction. And the sheer beauty of this is that by simply applying a tiny external voltage to this junction, we can artificially raise or lower that invisible electric fence, allowing us to turn the massive flow of electrons on and off at will. That precise on and off state, transitioning from abstract physics to digital logic, that is exactly how we generate the ones and zeros of all digital computing.
It is honestly mind-blowing to think that all of our modern computing power, from artificial intelligence to global telecommunications, all comes down to understanding and manipulating the microscopic gaps between energy bands in a tiny piece of doped silicon. We have definitely mastered inorganic silicon. But as we look to the horizon, to the fascinating dawn of organic semiconductors, conducting polymers, and molecular electronics, what impossible technology will we get to explain next? Thank you so much for exploring the fundamental quantum realm of the semiconductor story with me today. Keep looking closely at the world around you, keep asking questions, and I'll catch you in the next explainer.